I think that covers the sort of reasons for the torus, with the one exception of
the sevenness.
Which is the sevenness. Now, the torus is unique in topology and surfaces as requiring 7 colors to make a map.
Mm-hmm.
I think most people know about the 4-color mapping problem. On a normal surface, you cannot make a map that requires more than 4 colors.
And the rule being?
That no 2 countries should touch, no, 2 countries having a common border should be of different colors so you can distinguish them. Now the sphere you'd think would be more complicated, but it isn't. The surface of a sphere also requires only 4 colors.
Mm-hmm.
For example, if the sphere have a belt around the equator, those could be 3 different colors.
Right.
And then you can have the poles both a 4th color. That can be the same 4th color because the holes
because
don't
they're not
touch.
touching each other.
But in the torus, there's something goes up through the center of the hole so that the North Pole and the South Pole do touch. And you can show, if you're more careful, that you need more than 5, you need 7, but you don't need more than 7.
Mm-hmm.
And this one is painted in 7 colors. And if you look at it, you'll see, let's say the green...
Don't touch the microphone with it.
The green is surrounded by 6 other colors. Yellow, dark red, orange, and then you see this brown and blue. They're all touching the green.
Wait,
So
Arthur, let's wait for this. Let's do this again. Okay. Take 2.
Shall I start over?
Just start over this.
The green, take for example the green, it's touching all 6 other colors. On this outer edge you have yellow, red, you see the red? I should show it. Orange, brown is still touching the green, and blue. How many is that? 1, 2, 3, 4, 5. There's got to be another then.
Touching the green.
There's the purple.
Mm-hmm.
That's the 6th color, so we've got 7 colors.
Right.
Now there's nothing unique about the green, because if we pass on to the next one, say this orange, the same holes for that. It's surrounded by 6 others.
Mm-hmm.
So there's your map, your 7-color map. Well, people I mention that to would say, oh, but that's trivial. That's just an accident or something.
Mm-hmm.
It's not an accident. It's not trivial. It's because it's a different kind of surface, and you could say the colors are superficial or trivial, but they represent differences. The colors are not just colors. They're ways of representing difference. You get exactly the same problem if you try to join 7 points. You can't do it on a plane. So it's the same as the color problem, without the lines crossing.
What would be the distinction, though, or what would be the importance of this distinction? No, here, the question I want to ask is, these colors are all the same. I mean, they're different colors, but they don't have different qualities.
Right.
And yet, when you divide the universe into 7 stages, each stage has a different quality, and there's a sequence to them. There's this descent and the ascent.
Well, that takes us rather more deeply into it than I generally go, but it's described in the book where I show that the geometry of 7 elements, this was described by Veblen and Young, no relation to me, but long ago. Its projective geometry carried 1 step further. Normal projective geometry requires 6 elements or 6 postulates. There are 7 postulates in this projective geometry of Veblen and Young.
Mm-hmm.
And those postulates have a direct correlation to the powers. That's shown in the book.
But it doesn't correlate back to the torus and the 7 colors on the torus. So, I mean, that's, in a way, that's a different 7. I mean, I don't mean to be pressing you too hard on this, but, you know.
The set of 7 elements is equivalent to the torus.
I mean the elements don't have these distinctions either. The 7 elements don't, in and of themselves, have these distinctions. They can be A through F or G or whatever. But
you're representing the elements by numbers or letters or colors.
And or colors.
But the powers that the elements have are sequential. Now, it's not. You might have started with the wrong one to call it 1, but that's open. You find that when you describe these powers, they have these when you the postulates have the character that describes the power.
What are the examples of a couple of postulates?
Well, let me give you one, because it was the extra one that they introduced.
That Veblen and Young introduced.
Yes, which let me go back a little, because I haven't even said what the postulates deal with.
Right.
The postulates deal with subsets in the set of 7 elements. Now, they don't start with 7 elements. They start with these postulates. They call the universal set U and the subsets, well, say S. And then it goes on to say there must be at least 3 elements in a subset. And there must be no more than 2 elements.
More than one
Each element must be in at least 2 subsets. Things like
These
that.
are the postulates.
Yes.
Okay.
I could read them off and get them right the first time,
no, it's
then
not
you
important.
wouldn't remember them.
But what you're saying is that there's a correlation between these postulates.
Right. Well, I'm taking the one that I place 5th to illustrate.
Okay.
This is the one that says there can be no more than 3 elements in a subset. Now, the difference, that's the one that's different from the 6 of projective geometry. Projective geometry lacks that, so there can be any number of points in a subset. But if you've ever tried to find, say, 3 points collinear, you find it's impossible. And similarly, 3 points define a circle. If you try to find one more on that circle with absolute accuracy, it's impossible. So it makes sense to have no more than 3 elements in a subset. But the result of that, instead of being a constraint on the system, tends to make more subsets. In other words, it's like having a law that you couldn't have more than 3 people in a house. This would mean that you have to make more houses. So it correlates with the principle of growth in the
okay, so this
theory.
Correlates with the 5th, and the other postulates you're saying correlate with the others.
Yes.
This is in the book?
Yes.
Okay, then we'll refer people there.
Well, what did we get into this? We're still talking about the torus, and you were asking why did the colors, which are more or less co-equal, correlate with these powers, which are so different.
Right.
Well, I just have to refer to the book for that.
Okay. Gee, I want to know how to tie this up and tie this together. We've covered so much ground.
Well, we've covered everything except one point that I think is most important, and is the final clincher for 7. That if you make sets of an arbitrary number of elements, and then examine how many subsets you can have, because subsets have the property of connecting with each other and making things interesting. You find, for instance, with 4 elements, 4 points, you can only have one subset of 3. Because then if you use the other
then they'll have more than 2 in common.
Have 2 overlapping.
2 in common, right.
And 5, you can get 2 subsets, but no more. 6, you can get 4 subsets.
Okay.
When you get 7, you can get 7 subsets. When you take 8, you can't get all subsets to connect with each other, and the thing breaks in 2. This is something, it's a fun thing to do. You do it with points or letters and try it out, and you'll see for yourself.
So you're saying the 7 is as complex as things can get before they fall apart.
It's the richest number of elements out of which to make a universe. More, it won't work, and less, it's not so rich. So I would think that if, it's sort of a Murphy's law in reverse, that if a thing can be complicated, nature will make it so, or something like that.
Mm-hmm.
If there's an opportunity to make it complicated, nature will take advantage of it. Or nature will take advantage of the richest system that it can avail itself of.
Right.
You can say, well, suppose it doesn't. Okay, well then it hasn't evolved to its full potential. And that would explain why earlier principles try to get to be more than they are.
Mm-hmm.